Hello, and welcome to tutorial number 2 of the SIBGRAPI 2020. My name is Theo de Campos, or Teófilo de Campos, but I prefer to be called Theo. I'm a professor here at the University of Brasilia. Well, before this, I worked in several places. I spent about 15 years in Europe, mostly in the UK, where I did my PhD, and so on. But well, anyway, this is not about me. So this tutorial is going to be presented by Felipe Cordeiro, and he's co-authoring this tutorial with Gustavo Carneiro. Right? Felipe is a professor. I'm quickly going to go through his bio. He's a professor at the Department of Computing at the Federal University of Pernambuco, Federal Rural University of Pernambuco, right? UFRPE. He's been there since 2011, when he joined as a temporary professor and then became an adjunct professor in 2013. In 2015, he got his PhD in computer science from the Federal University of Pernambuco, UFPE. And in 2019, he moved to Australia. So he joined the Australian Institute of Machine Learning, AIML, at the University of Adelaide as a visiting professor until a few months ago, I understand, right? A couple of months ago. You can obviously tell more about that. And he's specialized in the area of this tutorial, right? Noisy labels. Where he developed some work on at the AIML. They recently submitted a paper to ACCV, and he has worked on computer vision, medical image analysis, and machine learning. So, as I mentioned, this work is co-authored with Gustavo Carneiro, who is a very well-known researcher from Adelaide University, the director of the AIML, and he's got, I believe, nearly 7,000 citations or something like that. And so he has been at Adelaide since 2011, and when he became an associate professor, actually he became an associate professor in 2015, and a full professor last year, 2019. So he spent he went to the Technical University of Munich a couple of times in 2014 and 2019 as a visiting professor and a Humboldt fellow, which is quite prestigious. And before that, right? So from 2008 to 11, he was a Marie Curie IIF fellow and a visiting assistant professor at the ITS, or Instituto Superior Técnico of Lisbon, in the CMU Portugal Institute. And before, from 2006 to 2008, he was a research scientist at Siemens Corporate in Princeton, USA. In 2005, he was a postdoctoral fellow at the University of British Columbia, and then at UC San Diego. He got his PhD in 2004 in Toronto. And well, he has been doing lots of different things in machine learning with an interest in computer vision, medical image analysis, and so on. Unfortunately, as I understand, Gustavo is not actually going to present the tutorial. I guess one obvious reason is the massive time zone difference. But of course, Felipe can tell us more about that. So anyway, I'll pass the word to Felipe, and then after that, we can actually start transmitting the presentation. Felipe?
Okay, thank you very much for the introduction. Gustavo, he must be sleeping now at this time. It should be like 3 a.m. in Australia, so he's not participating, but he helped to develop this tutorial. And Theo introduced me and Gustavo very well, so I don't have much to add. I've been working with noisy labels in the last years in the Australian Institute of Machine Learning with Professor Gustavo. And we have just beat it state of the art, and we just got a paper accepted in WACV conference. We had the best results, and we are submitting another paper for CVPR next week. So we are very aware about what is the state of the art of noisy labels and what are the current approach that people are developing and future trends for the next year. So I've pre-recorded all the tutorial because I was afraid of my internet connection. So I just pre-recorded everything, and the staff can start now. Thank you very much. Hello everyone. I'm going to present a tutorial how to train a model when you cannot trust on the annotations. The authors of this paper are Felipe Cordeiro, that's me. I'm a professor from Universidade Federal Rural de Pernambuco. And the second author is Gustavo. He's a professor from University of Adelaide in Australia. All the material from this tutorial, the slides, codes, and link to the paper, you can find at github.com/philippe-research/tutorial_noisy labels. On our GitHub page, you can find the codes folder, slides folder, and also the link to our paper. In our paper, you'll find a survey on deep learning with noisy labels, and you can find all the related work, definitions, and results from state-of-the-art that we will also present during the tutorial. In the first part of the tutorial, I'll talk about motivation and why you should consider the presence of noise labels when you train your model. And then I'll talk about definition fundamentals, such as noise rates, open set noise, closed set noise. And then I'll talk about all the related work from the last 2 years. And in the second part, we'll have some practical examples with code demonstration, where I'll help you to build a benchmark with synthetic noise for evaluate your models. And as well, we will implement some practical solutions that you can easily adapt to your models. And in the end, I'll talk about some recent approach, trends, and opportunities to work in the area. And as main motivation, we have that state-of-the-art models, they usually require large amount of clean and annotated data. We know that unsupervised training, it has grown in the last years, but the supervised model is still the best approach for most of the data sets. And when we think about training a data set in a supervised way, we usually think if the data is annotated, we assume that the data is clean. However, that's not true, mainly when we consider large data sets. When we think about a large data set, the first data set that comes in mind is ImageNet. ImageNet is one of the largest data sets that we have available. It contains around 15 million labeled images with 20,000 different classes, but it took around 2.5 years to be complete, and it needed the help of 49,000 people from 167 countries. So it was very expensive, and it took a long time to be completed, and it had to be labeled by many people and reviewed, and they had to pay attention if the label was correct or not, because it was going to be published. So it had a lot of effort involved to build a data set of this type. And even with all this effort, it is still possible to find some labels with wrong annotation. But usually we don't have all this structure and money to invest and people to help you to build your own data set. So there are a lot of challenges related to time and costs that make it difficult to build your own data set. So when you think about building a data set or using some data set that's available, usually people don't care much about checking how clean is the data set. They just build the data set and train the model, and they assume that if someone labeled it, being a specialist or not, so it's fine, and that's enough to train a model. And because you are using deep learning, that will work, and you don't need to care much about that. So just to fine-tuning the parameters of the model, that's okay. But actually, building a clean data sets is very difficult. When annotating data sets, we basically have two options. First one is to use a human annotation, and second one is to use an automatic or unsupervised annotation. The problem of using people to annotate, to have human annotations, that always there is the risk of human failure. Humans can get distracted and can make mistakes, and they will make wrong labeling, will have some kind of noisy labels. And by using automatic methods, it's hard to find automatic or unsupervised methods that have labeling accuracy comparable to humans, mainly when it's related to difficult tasks. When we think about manual annotation, either by using crowdsourcing or just by manual annotating, we usually think about having easy images where the user will look to the image and easily identify if it's a dog, it's a cat, if it's an owl. So we usually don't have this kind of scenario where it's very easy, but even when we have, if we have a large amount of data, we still can have some problems. So we can have mistakes caused by misclick, or maybe the user is not receiving any salary for doing the annotation, or maybe he receives, but he receives the salary based on the amount of image that he labels, not by the quality of the labeling. So it's very hard to check this kind of problems. And we also have problems related to the quality of image. If we have a low quality image, like these are images from CIFAR-10, they are very small, and for some cases it's very difficult to identify what is the class of the image. So for example, here we have an image that can either be a dog or a deer. It's difficult to identify. Here can be either a cat or a dog. So sometimes the quality of the data provided to the user is not enough to provide an easy classification. And also we have challenging tasks, such as in the medical field. Here we have mammography images and dermatoscope images. So even the specialist, even the doctor would have some challenges to try to label everything, to identify if the images are benign or malignant. So even between specialists, they can have different opinions. They can say that's benign when it's malignant, and they can have conflicting opinions. So that's very likely to have some kind of noise labels at some degree. So in general, we always will have some kind of initial data set that's unlabeled, and we want to label it. So we have the options of using crowdsourcing, find some specialists to annotate, or using some unsupervised model. But it's very likely in the end, using any of these strategies, to have some kind of noise labels, to have images with the wrong label, like if the image is a plane but the label it's a dog, or if it's a bird. Usually it's very likely to have wrong labels between plane and bird, or between car and truck. That's a common mistake for CIFAR. So if you have noise labels by the end of your labeling process, if you want to remove your labels, you would have to have an additional effort to have a second round of labeling or to review carefully all the images. So it takes more time, it adds additional costs. So the ideal scenario it was if we could have some kind of unlabeled strategy or a very simple labeling strategy that in the end it could generate some noise labeled image, but it is still be fine for training our models. But the main question is, why having noisy labels is a problem when training deep learning models? So a paper that answered this question very well is this paper, Understanding Deep Learning Requires Rethinking Generalization. That's from ICLR 2017. I'll show this paper. This is the paper. This paper is from Benju, and they are from Google. And that's a very interesting paper that they claim that deep neural networks easily fit random labels. And they do some experiments that show that, and I'll show that. So here is the main experiment that they do. That's a very interesting experiment. They basically train deep learning architectures for CIFAR10, and they analyze different kinds of noise. So they try noise on the image, noise on the labels, Gaussian noise, and they compare to the original data set with clean labels, no noise. And what they try to do is to achieve 100% accuracy in the training. That it means that the model memorizes all training data. So they want to see that if the model can memorize the training data, even in noisy conditions. So here they have the training iteration, training steps, and the average loss. For the clean data set using the true labels, they can easily have a loss close to zero, achieving 100% accuracy for training set. And when they add noise on the image, it's a little bit harder, but they still can do that with random pixels, with Gaussian noise. And the hardest one is using random labels. That means that the noise is only on the labels, not on the image. And even having noise on the labels, the model can memorize all training data and achieve 100% accuracy. But what's the problem about memorizing all data? First, having 100% accuracy in the training data, that doesn't mean 100% accuracy in the test data. And here, although they have a training loss close to zero and have a high accuracy in the training data, when we look to the test error, here they show the test error having 0% label corruption for different architectures. So they test for MLP, AlexNet, and Inception. And for Inception, for CIFAR10, it's very close to 0% error. Actually, it should be 95, 96, and for zero label corruption. And when they increase the noise rate close to 10%, the test error increase and goes to 90%. In the end, it's 90% because it's CIFAR10, so there are 10 classes. So it's a random guess here. So what the paper shows is that even having noisy labels, even having labels that they are random, but they are not related to the image, like an image of a cat can have a label of a truck, an image of a plane can have a label of a dog, And it's not related the label and the image, but even having the random labels, the model can memorize all the labels and can fit to the training data. And here in the end, they show a table that they show that they can reach 100% accuracy for all the models, and even having random noisy labels, they can reach 100%, but the test accuracy decrease a lot. So in this paper, they show that the deep learning models that we have, they are not robust to noisy labels. And by increasing the noise rate, the amount of noise, it decreases the accuracy in the test data. So it shows how important it is to try to start using some approaches that are robust to noise labels. Because when we use large data sets or when we build our own data sets, we don't care much about noise rate, about noise on the labels, but that directly affects on the performance of the deep learning models. So that's why it's important to use our methods or some training strategies that are robust to noise labels.
Olá. So is this the...
I will talk now about
It's correct.
definition and taxonomy related to noisy labels.
Será que faz uma pausa agora? Hi. I think, yeah, this was very interesting, very good introduction and an extremely relevant problem. And I'm not sure if you're still gonna talk about it in the next bit of the presentation, but I saw that they deal with hidden labels, or actually say, well, they have a data set of noisy labels or hidden true labels. I wonder how they collect that. They need someone to double check all the labels and then annotate which ones are wrong so that they can learn on it?
Yeah, actually, they can initialize with a clean data set and add synthetic noise, so they have control of it. Or they just can have a data set collected from web and they don't have control of anything. But I'll talk about the data sets and noisy types in this next video.
All right, that's great. I'll just have a quick peek. All right, I don't see any new question. So yeah, we can carry on. Thanks.
Okay, thank you.
I will talk now about definition and taxonomy related to noisy labels. When we talk about noisy labels, it means that the label that we have for the image is wrong. So it's different from the true class. So here, for example, we have the image from a dog, but the label it's a cat, so it's incorrect. And when we talk about noisy labels, we mean the noise is only on the label, not on the image. So the image has no noise, or it can have, but we refer to noisy label as a wrong annotation, a label that's incorrect. Here, for example, we have an image that we call an image X. And for each image, we have a hidden clean label that we define as y hat belonging to gamma, that's a set of possible classes. And this is the true class or the hidden class or the ground truth class. There are different names that we can call. And we also have the observed label. The observed label are the labels that we have access. So when we have a data set, the hidden label, the true label, sometimes it's unknown. We don't have access to it. and we just have access to the observed label. So here, for example, we have the observed label, it's a dog, and the hidden label is a dog. So that's a correct labeling. And here we have an observed label, it's a cat, and the hidden label, it's a dog. So this is a noisy sample with a noisy label. We define a data set of noisy labels by D that contains a pair of xi, yi that are the observed labels, they are not the true labels. Then we have an image xi, the observed label y, and the hidden true label y hat. All the observed labels, they follow a distribution given by the posteriori probability of y given xi, the set of possible classes gamma, and y hat I. So for the posteriori probability of having an observed label equals to class J, given xi and y hat I equals to class C, this probability is represented as the probability eta of the observed label J and the true label C of the image xi, and the summation of all the observed labels to the class C of xi, it's equals to 1. So if we represent all the probabilities between the different labels, we can build a matrix that it's like this. This we call the transition matrix, that it maps the noisy process between all the labels. So we have the true labels and the noisy labels. In this context, we are considering a problem with 5 classes from labels from 0 to 4, and each cells represent the probability to map from a true label to a noisy label. So here, for example, if we have a true label 1, it has 80% probability of having a correct labeling to the observed label. And it has, for example, 10% probability of having a true label 1 of class 1 mapped to class 0. So for each true class, the summation of the column should be equals to 1. And for each cell, we have the representation of eta. For example, here we have the noisy label 2, the observed label 2, given the true label 3. So it has 60% probability of having this mapping. When we talk about noisy labels, there are 4 types of noise that are frequently studied in literature. These noises are symmetric noise, asymmetric noise, semantic, and open set. The symmetric noise is a random transformation from the true class to the observed label, to the noisy label. And it's also called random or uniform. So for each class, the class has equal probability to flip its label to another class. For example, here we have the picture from a cat. So if the class is a cat and it has a chance of having a wrong label, this probability will be equal to every other class from the problem. So it has a probability eta to flip its labels to a dog class and probability eta to flip to horse. So if we have a probability eta equals to 40% for symmetric noise, it means that every label, it has 40% chance to flip its label to another class. And when looking to the transition matrix, the probability of the observed label be equals to the true class, it's 1 minus the noise rate. For example, if I have label 2, it will be mapped to the observed label. It has 6% of probability of having the correct label. And the probability of an observed label J and true label C, it equals to the probability of the symmetric noise. And the probability of having an observed label J and a true class C, it equals to the probability of the symmetric noise divided by the amount of classes minus 1. So for example here, the probability of having the observed label 2 and the true class 1 is equal to 40% divided by number of classes 5 minus 1. So in asymmetric noise, every time that a true label flips to a wrong class, it has equal probability to flip to a different class. The symmetric noise doesn't represent much the real noise scenario that we might find when building a custom dataset, but it's the most basic type of noise that usually people start evaluating the models with the symmetric noise. That's the simplest one that we have, and then start evaluating for more difficult types of noise. Here I show the feature representation of a model training with symmetric noise compared to a model training with a clean data set. So this picture represents the plot from the TSN plot that we have the feature representation. The picture from the left is with a model training with a clean data set. I think it's CIFAR 10. It has 10 classes. And in the end of the training, it has a feature representation with different separated clusters for each class. That means that the model can learn well the representation of each class. And the picture from the right shows the features training with a data set with symmetric noise. So by the end of the training, we still have the clusters with for each class, but within the clusters we have some samples from other classes. These are each color represents the true labels. So when the model look to the samples, for example, all the samples from each cluster are from the same color. For example, here we have the orange cluster. For the model, the observed labels, everything here would be orange. But the true labels, when we look at the true labels, they are from different colors. That means that shows what we saw from the paper, that in the end of the training, use symmetric noise or any kind of noise, the model can learn similar features between different classes. So if we have a cluster that represents a car and we have noise labels from cars mapped to dogs or cats, it can find somehow similar features between cars and cats and cluster them together. So that's how it looks like in the end. And for asymmetric noise, it's when the noise labels happens only between similar classes and just a few classes. For example, if we have a data set from, this is CIFAR 10, we would have noise labels from the true label truck mapped to automobile. They are similar classes. From label bird to label plane, and from label deer to label horse. So these are similar classes, and this type of noise is more realistic. So it's the type of noise that we can find when building data sets. In the asymmetric noise, the probability is class conditional. So if we have this example with 5 classes, only a few classes will have a mapping from the true label to the noisy label. So for example, from the true class 2, it has 6% probability of having the same class, but 40% probability of being mapped to label 0. And for the other labels, it's 0% probability. So there's no mapping from 2 to the other to the other labels. And when we look to the TSN plot from asymmetric noise, it is similar to the symmetric noise, but it shows that the noisy labels, it happens only between a few classes. We don't have that random scenario from the symmetric noise, and the model still can memorize, but it happens only between similar classes. And the semantic noise, it's a kind of asymmetric noise, but it doesn't depend only on the class, but it depends on the class and the image. So it depends on the class, the observed label, the true label, and each image from the data set. So in the asymmetric noise, we had a mapping from class truck, for example, to automobile, let's say with noise rate 40%. So all the mappings from truck to automobile, it happens with 4% probability. But with semantic noise, it happens depending on the class and on the image. So we could have, for example, a truck 1, it's mapped to automobile with probability 42%, but an image of truck 2 be mapped to automobile with probability 38%. So it depends on the image. And this kind of noise, it's even more realistic than the asymmetric noise. And this kind of noise is not much explored in literature. It's one of the most challenging type of noise. And it can be easily generated by some kind of automatic labeling method and unsupervised model. If you use some kind of unsupervised model to label everything, it probably will have a semantic noise associated. So it will be very difficult to try to clean the data set. And at last, we have the open set noise. So all the other types of noise that we have seen, we were considering the closed set scenario. That means that when we have a wrong annotation, when I have a noise on the label, the wrong label, it is from all the known classes. For example, if we are working with CIFAR10 and we have a noisy labels, the noisy labels belongs to the 10 classes from CIFAR10. This picture here shows a representation of a problem, a binary problem that we want to classify a picture as a jasmine or a cat. And we have the samples that are labeled, that are cat and labeled as a cat. So those are clean samples. They have clean labels. And we have the pictures from cats labeled as jasmine. So they are noisy samples. And also we have pictures from jasmine labeled as jasmine. They are clean. And pictures from jasmine labeled as cat. So they are noise. But these noisy samples here from the cats and the noisy samples from jasmine, both are labeled from the known class, that's jasmine or cat. So they are closed set noise labels. But we can also have scenarios where we can have images with true label that's not known, and they are labeled as cat or labeled as jasmine. For example, we have the picture of a dog, and the dog class does not belong to the binary problem that is jasmine and cat. It belongs to a different unknown class. So it's considering open set noise label. Here I'll show how easily to have open set noise labels when building a data set. So imagine that we want to build a data set to classify types of shock or shock and another class. So if we want to build a data set collecting the results from Google Image, and we just pick up all the images, we'll have some images that are from class that are not from our problem. So if we have a problem to classify types of sharks or shark and another animal, this image here represents out of distribution sample. It represents an image with label that does not belong to our known labels for the model. So this would be OpenSet label, an image from OpenSet, this one as well, maybe this one. So we can find a few images easily just by searching for shark. We can find some OpenSet samples. So that's a common problem when you have data sets that are built from collecting images from the internet, and it's also a difficult type of noise, but it's very realistic. I'll talk.
Hey, right. That was a very interesting taxonomy types of noise and so on. And indeed, semantic noise is definitely the one I come across more often. And I think that's right. I guess so. Next, well, we're gonna have a break very soon. And next, Philippe is gonna, well, we're gonna, after the break, we're gonna carry on with this, showing the data sets. I'm not sure if Philippe has any comment before we go to the break, but I just, yeah, I mean, I'm gonna try and share my screen very quickly, but you know, Philippe.
Okay, thank you. Well, the idea was to show the types of noise that people use when evaluating noisy labels. So we have this main type of noise, the symmetric noise, that's the most basic one. That's very easy to deal, but people should evaluate this one. But the more challenges are the asymmetric and the semantic noise, and it's still an open issue in the area.
Nice. So I'm actually, all right. I think I'm actually trying to share the screen here, but essentially it doesn't. All right. Okay.
I think it's good.
Excellent. So yeah, I just wanted to. Well, I know this has been mentioned in the beginning, but I just wanted to bring this up again. And I even posted it as comment in YouTube. But so the material of this course is all available from this GitHub repository.
Yeah, on GitHub page you can find all the slides that I used for the presentation.
Yeah.
And also the code that we will use in the last part of the tutorial, where I'll show some code and run.
As well, yes.
Yeah, it also has the link to the paper.
Notebooks. So,
Yeah.
yeah. So I thought it'd be nice to bring that up. Sorry, I interrupted you, but carry on.
That's it. You can find all the material that I used for the tutorial, and you can replicate all the code and run and have the same results that I'm showing here. So I'll run this code and show everything, I think, in the last part of the tutorial. So after the break, we'll continue with the data sets, and I'll talk about state-of-the-art. And then in the third part, I'll show some code and show some solutions for noisy labels.
Okay, so I'll just thank the hosts for showing the link right here. And I guess we can go for the break and come back soon. Thanks.
Okay, thank you.
that's it. All right. I'm not sure if what I just said was broadcast or not. But anyway, in case it was not broadcast, welcome back to the tutorial on noisy labels by Felipe Cordeiro. We're gonna carry on. He's going to present the data sets used for this problem and then follow up with the rest of the course, the tutorial. And questions are welcome. We're gonna keep an eye on the in the chat in YouTube. And we can stop if we find a question that needs debating here. Right, so I guess, I don't know, unless if Philippe wants to say anything.
No, that's fine. If anyone has any questions during the presentation, you can ask in the chat, and we can pause the video and answer any questions that appear.
All right, so let's continue.
Distribution with lower 100, that's for noise, and a difficult type of noise, but it's very realistic. I'll talk briefly about the most used datasets for noisy labels. The most used dataset for used as benchmark for computer vision models is CIFAR10 and CIFAR100. And for noisy label context, what people do is, because they are dataset with clean labels, clean annotations, they add synthetic noise to evaluate their models. The CIFAR10 and CIFAR100 are datasets with 50,000 training images and a test size of 10,000 images. The image size is 32 by 32, and CIFAR10, it has 10 classes, and CIFAR100, 100 classes. So usually people add symmetric noise or asymmetric noise with different noise rates to evaluate their models. If you want to publish any paper with noise labels, you have to use at least some kind of real-world data set that contains real noise. So one of the most used is Web Vision. It contains 2.4 million images. They are crawled from Flickr and Google Images, and they have the same classes as ImageNet. They provide a clean test size of 50,000 images, and the training set estimated noise is around 20%. This data set is very challenging, and it's very difficult to fit the model to the data. Another commonly used real-world dataset is the Clothing 1M. It contains 1 million training images with 14 classes and a test size of 10,000 images. It also contains a clean training set. I think it's around 50,000 images, but it has a noise training set of 1 million images. The estimated noise for Clothing 1M is around 38%. And we also have Food 101, that is based on original Food 101 dataset. That's a clean dataset. They just built another dataset that was built collecting images from internet, and the difference is that it's a noise dataset and has more images. So it has around 310,000 images with 101 classes. And the estimated noise is around 20%. So these are the most used datasets. They use CIFAR, Web Vision, Clothing 1M, and sometimes they use Food 101. And if you want to propose some new model or evaluate something with noise label, you should consider different scenarios for synthetic noise used for CIFAR10 and CIFAR100, and also use a real-world dataset, a large dataset, such as Web Vision, Clothing on M, or Food 101. Now make a literature review. I'll talk about the last papers published for noisy labels in the last years in the biggest conference. And one interesting thing that we can see is that there's a growing interest in the area as the number of papers related to noise labels, they increase year by year. So in this graph here, it's updated until the end of first semester. So probably by the end of this year, the amount of papers, published papers, should be higher than last year. But there is a growing interest in the area of machine learning, of researchers publishing papers related to noise labels, proposing robust losses, robust training methods, and big companies, big players are starting to enter in this area, like Google, Facebook. So this is an area that has grown a lot in the last years, and you will see that the level of the solutions and the contribution and the increase in accuracy, it changes a lot in a difference of 1 or 2 years. The main approach that we can observe that has been proposed, in the beginning, most of the methods were based on transition matrix methods and robust losses, and then more sophisticated solutions started to be proposed, involving sample weighting, sample selection, ensemble, and meta-learning. I'll talk about each of these different strategies, starting with transition matrix. Before I talk about each method, I just would like to show the state-of-the-art results. It's a kind of spoiler, but just to show you, to have a notion of how advanced is this area, and then I'll talk about each method separately. So these are state-of-the-art results from a paper published this year in ICLR 2020, and we have the results for CIFAR 10, CIFAR 100, Clothing on M, and Web Vision. So the state-of-the-art model that we have is the Vidomix. That's it's a combination of any training strategy robust to noisy labels. We have here different scenarios with different noise rates, from 20% noise rate to 90% noise rate, and even having 90% noise rate, in this case is symmetric noise rate. The cross entropy, it decreased a lot, the results from 86 to 42, but with the state-of-the-art model, they can achieve 76. So it's a huge improvement from 42 to 76. And even if we compare the state-of-the-art, the Vidomix, with the state-of-the-art from last year, it is a big improvement, just 1 year difference. And we also have the big data sets that it improves a lot compared to the cross entropy. So I'll talk about that, but just to show you how good adopting different strategies it can improve from cross entropy. First, I'll give a background, what is usually used for training deep learning models. In general, people train regular deep learning models using cross entropy that is represented by this loss here, where HI is softmax output and YI is the observed label. And when we train a model with cross entropy, usually we can see this kind of behavior if we look to the clean and noisy samples. We don't have access to what is clean and what is noise, But if we had access, like if we generate artificially, synthetically, we can analyze the behavior of the clean and noisy samples. So it would have something like that. In the beginning of the training, the model doesn't fit to all the training. It's easier for the model to fit first to the clean samples. So usually the clean samples will have a lower loss in the beginning of the training, and later both clean and noise will have similar loss. So the model will fit to both kinds of samples. One of the first approaches that have been proposed for noisy label is the bootstrapping. And the general idea is to dynamically update the targets based on the current state of the model. So we have the cross-entropy laws that's commonly used. And what they propose is the bootstrapping laws. They propose the soft bootstrapping and the hard bootstrapping. So what they do for soft bootstrapping is like they use the as basis the cross-entropy laws, but they decrease a little bit the confidence of the observed label, and they give more confidence to the predicted label, the output of the softmax layer. So in general, what the model does with its laws is to encourage the model to be more confident on the prediction. So when we have noisy labels, if we use this observed label, it can be wrong. So I don't want the model to believe 100% in these laws. So what we do here for the bootstrapping laws is to decrease the importance of this observed label and give more importance to the prediction of the model, to make it be more confident about the predictions. And the difference between the soft and the hard is that for the hard bootstrapping, it uses the argmax of the model output. And when they use this kind of laws, we can observe this kind of improvement for the behavior of the clean and noisy samples. So usually it takes longer to fit to the noisy samples, and it allows the model to learn better the clean samples first. Another method is the forward and backward approach. It was proposed in CVPR 2017. And the general idea is that they try to estimate a transition matrix based on the noisy samples. So in general, we don't have access to the transition matrix because we don't know how the noise was caused. So what we can do is try to estimate. So I'll talk about how they estimate later, but the general idea is that once they estimate a transition matrix, they make some kind of corrections on the predictions. So they have the cross-entropy loss, and the output predictions, they correct it by the transition matrix. And they propose two different loss functions in the same paper. So this is the forward loss function, and this is the backward is also a cross entropy, but using the inverse transition matrix. So the algorithm of this approach is that you start having a noisy training set, and as the transition matrix is unknown, they have to estimate it. So how they do that? First, they train a neural network with the noisy training set and using any kind of laws, in general cross entropy, and based on the outputs of the samples, they estimate the transition matrix. And after that, after they estimate the transition matrix, they will retrain the model using the forward or the backward laws. And how the transition matrix is estimated? Well, the idea that they give in the paper is imagine that you have a perfect image or perfect representation for a class. For example, you have an image of an apple that's a very good quality and represents well the image. And if you have that image and you give to input to the model, and you observe the predictions from that image, the softmax score to the other class that are not Apple, they would give the noise rate related to the transitions from the Apple class to the other class. So the way that they get this ideal sample is to get the image with the highest classification for that class, with the highest softmax score. And based on that, they estimate the transition matrix. So the true transition matrix, the ideal transition matrix, would be a representation of the probability of the observed label given the true label. But we don't have this probability. So the estimated transition matrix that they propose in the paper, it's based on the softmax probability of an observed label given the input image. And this input image would be the good, it would be a sample with good representation that's obtained with the highest classification, highest softmax score. In their paper, they show results for MNIST dataset. A few years ago, people used to use the MNIST dataset to evaluate the models. In some papers from CVPR, they had results only for MNIST. But nowadays, people don't use MNIST anymore. They just use that dataset that I showed, CIFAR, Web Vision, Clothing 1M. But in this paper, they show that when using the cross entropy, if they increase the noise rate, the accuracy decrease, but with their loss, that's the backward or the forward, they can keep the high accuracy. When we talk about loss functions, there are several robust losses that have been proposed to address the noise level problem. One good aspect of proposed loss functions is that it's very easy to adapt any robust loss function to deep learning models. A very interesting paper that talks about existing loss functions applied to noise level problem is this paper that the title is Robust Loss Functions under Label Noise for Deep Neural Networks. It's from AAAI from 2017. And this is more a theoretical paper that it just analyzes existing losses commonly used for training deep learning models. So in this paper, they evaluated the categorical cross entropy, the mean square error, and the mean absolute error. So in their paper, they analyzed the losses for different data sets. And in this picture, they show the results for MNIST dataset in the first row and second row for the RCV1 dataset. And they test for different noise rates from 0% noise rates to 80% noise rate. And here is a class conditional noise, that's asymmetric noise. So in each picture here, we see the test accuracy in red for the cross entropy, and in green, the mean absolute error accuracy test. So what we can observe is that for low noise rates, the cross entropy, it has a quicker convergence, and in the end, it achieves a higher accuracy. For 0% noise, from this picture it's difficult to see, but there's a small gap between the test accuracy from cross entropy and the mean absolute error. And when we increase the noise rate, when we have more noise in the data set, usually the cross entropy, the accuracy drops a lot. Here it's in red. It in the beginning of the training it increased and then it overfits to the noise samples. But if we look to the mean absolute error, it has a higher accuracy and it's more robust to noise. So the higher the noise rate, the more we can see the difference between mean absolute error and cross entropy. And that also happens for the asymmetric noise. And this for MNIST and for the RCV1 dataset, we also can see that when we have high noise rate, the mean absolute error have higher results, but for low noise rate, the results from the cross entropy are much better than mean absolute error. So the challenging is to know when to use each one, because usually we don't know the noise rate of a data set. We don't have this information. So we could try to have some kind of weighting based on the loss on the training set. But the idea of this paper is to show that cross entropy loss is not robust to noise, and the mean absolute error is. And here in this table, they show the results for other data sets that they evaluate. They also evaluate for CIFAR-10, IMDb, and other data sets. And the MSE, it's always robust to noise rate. So when we have a higher noise rate, difference compared to cross entropy is very high. And for most of the data sets, the difference between mean absolute error and MSE, it's very low. There's a paper from this year that's the curriculum loss. It's a paper from ICLR from this year, and they first analyzed the 0-1 loss. That it is a loss that when the classifier has the correct prediction, it will have a loss equals to 0, and when it has a wrong prediction, it will be 1. So it is 0 or 1. And what they observe is that this kind of loss, it's robust to noise labels. And what they try to do is they do a little modification in this loss. They propose a tight 0-1 loss upper bound. And they call this curriculum loss because we can see that as a kind of weighting to the samples. You can have samples with 0 weighting. It's a binary weighting. That's why they call curriculum loss. And they compared to other proposals, and actually their proposal is the CL and NPCL, and they show better results and compared to existing approaches. Another paper from this year that proposed a robust loss is this paper that's normalized the loss function for deep learning with noise labels, published in ICML from this year. And that's interesting because they show that if we use a normalized loss, like a normalized cross entropy loss that will have a range from 0 and 1, it shows better results than just using a cross entropy. So here, for example, they show the results comparing cross entropy and normalized cross entropy that follows this equation. And they also compare the focal loss, that's another loss function, with the normalized focal loss. And they show an improvement when using normalized cross entropy and normalized focal loss. So with regular cross entropy, in the beginning of the training, it has a higher accuracy, but it overfits and memorizes all the noisy samples. While the normalized versions, it behaves more like a robust loss function. And when analyzing the normalized mean absolute error and the normalized, this is the reverse cross entropy. The difference is not as the cross entropy at focal loss. Actually, the results that are better here are the original version, not the normalized. So it doesn't work for all noise rates, just a few types. And based on that, they classify the losses in two types, that they call the active losses and the passive losses. The active losses, in general, they have better results with low noise rate or zero noise rate. And the passive loss, they usually are more robust to noise. But for low noise rates or zero noise rate, they are worse than the active loss. And what they propose is a combined loss, that's the active passive loss, that they just put weights to the active term and another weights to the passive term. So they try different combinations of these active loss and the passive loss. And in the paper, they show an extensive analysis of different losses and combinations. So they test the cross entropy, focal loss, generalized cross entropy. This is another loss that's based on negative learning. This is symmetric cross entropy, and they compare all these losses with the combinations that is the proposed active passive loss. And they test for different data sets, the MNE, CIFAR, and CIFAR10 and CIFAR100. And in general, they show that the combinations of active passive is better than just using the original version of the losses. And the best combinations are the normalized focal loss with the reverse cross entropy and the normalized cross entropy with the reverse cross entropy. The challenging of using these active passive laws is to find the correct weights for each term, the passive term and the active term. There are some approaches that use a combination of methods to try to make the training more robust to noisy labels. So one of the first approach that showed this concept was the MentorNet. It used two networks, the student network, that's a base deep learning model, and they have the MentorNet, that's another network that will try to find weights to give to the student network. So the idea of the MentorNet to use a curriculum learning strategy, that the curriculum learning strategy tries to find weights to the samples to guide the training, to train first the easy samples or the hardest samples, just to give a strategy of what samples the model should train first. So in this work, the MentorNet, it uses one network, that's the MentorNet, that will find a curriculum strategy to give to the student. So based on the features from the student network, it will find the weights and give it back to the student net. So this is done at every iteration. The student net trains the model with the noise data set, and in the end, the output of the networks, the features, will be given to the MentorNet, and then it finds the weights and keep training. So the idea of the MentorNet is to give high weights to the easier samples, to train them first, and in the late training to give the hard samples. The results of MentorNet show that this strategy of combining networks increased the state of the art compared to other strategies only based on the laws. Another paper that uses a combination of models is this paper, is decoupling from NIPS 2017. So the idea of the paper is to train two models in parallel and use the disagreement between the two networks to find the samples to train the model. So it is a different paper because it was proposed for an application of labeled faces. But the general idea of the method is that it will train the two models in parallel, and at every iteration, it will find that the labels with different prediction, that there is a disagreement between the two networks. And then based on these samples that have different predictions for each network, it will update only that samples. But this update is done separately. 1 year later, it was proposed the co-teaching algorithm that, as the coupling algorithm, it used two models trained in parallel, but the main difference is that each model is trained with the samples filtered by the other model. So, for example, here they have the algorithm, and at each iteration, it will obtain a subset of samples with small loss. So each model will have a different subset, and this subset will be used to train the other model. So when they do the update of the model, for example, if you have a model F and a model G, the model F, the weights of model F will be updated with the samples selected from model B. That's what we see here. So the network B, it's updated with the samples filtered by the model A, and vice versa. So that's a different strategy. And results shown by this paper showed a good improvement compared to the other methods. And in the next year, they proposed a modification to the co-teaching that was called co-teaching plus. And it has a similar strategy from co-teaching. The main difference is that the selected samples are not only based on the low loss of the samples, but also based on disagreement. So using samples that have disagreement between the two models, it increases the results. Because when they use co-teaching, they saw that many times they shared similar samples, and in the late training, it converged to have always the same sample selected. So what they propose to do is to use the samples that have small loss but also have disagreement with the other model. And also they compared the co-teaching plus with co-teaching, the MentorNet, decoupling, and F-correction. And they show that in general, the co-teaching plus have better results for low noise rate and higher noise rate for MNIST and for CIFAR. Another interesting method is the joint training method. It was published on CVPR, and it has the same idea of using co-training, but they add contrastive loss in the middle. So they have the two models trained in parallel, and they have the loss from the first model, the loss from the second model, and they add a contrastive loss. Results showed improvements over the co-teaching strategy using the same model for CIFAR 10 and clothing 1M. A different strategy for noisy labels is the use of negative learning. This is one of my favorite strategies, and unfortunately it's not the state of the art anymore. It was until the beginning of the year, but I found the idea very interesting. The idea of negative learning is, instead of teaching the model what is the class, we will teach the model what it's not. For example, if we have a picture from a dog and we have different other classes like car, cat, and other thing, I would tell the model, this is not a car, or this is not a cat, or this is not a horse. So why is this interesting? Because if we have an image with noisy labels, and if we have to make a guess to give to the model, it's easier to guess what the image is not instead of saying what it is. For example, if we have a problem with 10 classes and we have to guess what class is, we have a chance of 1 over 10 possibilities. And if we predict what it's not, we have a chance of 9 over 10 of being correct. So in negative learning, we will have negative learning laws that it's based on we say the negative label, that means what the label is not, and that's selected randomly. So in the beginning of the training, for each label, they will find a negative label that they call the complementary label. They randomly select from 1 from C, excluding the observed label. And the negative loss, it's based on this complementary label and the log of 1 minus the output prediction of the model. And the training strategy that they propose in this paper is that they first start with the training of negative learning. They have a negative learning training that they use the negative loss. And after that, they have a filtered negative learning that they will have the negative learning only with the samples with a small loss. And after that, they will use a positive learning, that's the traditional learning. And one thing interesting about using negative learning is represented by this picture that they show in the paper. And here we have the histogram of clean and noisy samples by the end of the training. So in this first picture here, we have the histogram when using the standard positive learning. The picture B here, we have the distribution using the negative learning. The third picture C here, we have the distribution using the selected negative learning, like the filtered negative learning, and in the end, using all the process that they propose in the paper. So we can see here that we can easily split the noisy and clean samples by using this strategy. And in the paper, they showed that this strategy provides good improvements over existing state-of-the-art. Data augmentation is also a useful strategy to combat noisy labels. Some recent approaches have started to use data augmentation methods, and one of the most used is the mix-up. The mix-up algorithm, it was not initially proposed for noisy labels. It was more a new data augmentation method. It was proposed 2 years ago on ICLR, and it's a very simple idea for making data augmentation. So basically what they do for mix-up is just a linear combination between the input and between the labels. So for example, if we have an image x, xi, and another image xj, it will combine these two images, making a linear combination to generate a new image. And they also do that for the labels. So for example, if I have an image of a dog and an image of a person, it will combine based on a parameter delta to generate the new image. In the paper, they provide a code for implementation in PyTorch, but it's very easy to adapt to any code. The idea of mix-up is that by doing linear combinations, it encourages the model to have a linear behavior between samples of different classes, mainly between the regions of border. For example, when not using mix-up, the areas that are far from the training points, they will have more oscillations between the predictions. And when using mix-up, it will have a more constant behavior between all the samples. And in the original paper, they also evaluate mix-up considering a corrupted scenario where we have the noisy labels. And they show that when using mix-up, it increases the accuracy, making the model more robust to noisy labels. After mix-up was proposed, almost every recent method have adopted the mix-up data augmentation. A paper from Arazu from ICML 2019, it uses mix-up, but they also propose an interesting solution to try to identify clean and noisy samples. Although several methods have used the loss function to try to separate clean and noisy samples during the training, this strategy that is known as small trick loss, it has some limitations. For example, we might have some hard clean samples that do not fit the model during the first stage of the training, and they will only fit in the middle to late stage of the training. And as well, we might have noisy samples that have very similar features to clean samples. So they would be hard noise samples that they would easily adapt to the model during the beginning of the training. In Arazo's paper, he proposed the use of two-component mixture models to try to fit the two distributions. So the distribution with lower loss will be classified as clean, and the other one will be classified as noise. In their paper, they use a beta mixture model and a Gaussian mixture model, and they conclude that the beta distribution works better. But recent papers have started to adopt the Gaussian model as it seems to work better for general case. In Arazo's paper, they use that bootstrap loss, but using the probabilities provided by the mixture model. So the samples with higher probability of being clean will trust more on their observed labels, while the samples with higher probability of being noise will trust more on their own prediction. By using this strategy of mix-up and bootstrap loss, they can achieve a good split of clean and noisy samples. However, this doesn't seem to work very well for higher noisy rates such as 50%, 80%, and asymmetric noise. In my opinion, this paper showed how good mix-up data augmentation is for noisy labels. Even using the mixture models and the bootstrap, the results would not be so good without using mix-up data augmentation. Before talking about the next model, I need to talk about the mix match that was a solution proposed for the semi-supervised context. So we have this paper mix match that they propose a solution for semi-supervised problem. It was published last year on NIPS, and it was proposed by Google team. One of the novelties of this paper is try to estimate the labels from the unlabeled samples in a self-labeling approach. So in their strategy, they generate several different data augmentations and calculate the average of the predictions. After having the average, they do a sharpening process to improve the confidence of the predictions. In the mix match algorithm, they initially have the labeled dataset X and the unlabeled dataset U, and they combine them using mix-up to generate two new sets. And then they will have different laws from the new labeled set and the new unlabeled set. The mix match algorithm is very simple, and the basic idea is that they combine the labeled set with the unlabeled set using mix-up operations. So they do that linear combination between the image and between the labels. And as the unlabeled set doesn't have labels, they use the predictions of the combination of data augmentation. And in the results, they show that they can achieve high accuracy even using just a few labels. This is the error for CIFAR 10. So why is this paper so relevant? The main thing is that this paper draws attention to people look to the noisy label problem as a semi-supervised problem. So if we can find a subset of reliable labels, or if we have a very small clean data set, all the other noisy samples, we could look at them as unlabeled samples and treat the model as a semi-supervised problem. The main difference between a noisy label problem to a semi-supervised problem is that in a semi-supervised problem, we know what are the clean samples. And for a noisy label problem, we don't know what's clean and what's noisy. The state of the art that we have for noisy labels until now is the divide mix. The divide mix deals with the noisy label problem in a semi-supervised way. The paper itself is not very original, it's just a combination of other methods already published. So divide mix, it used the co-teaching approach, it used the GMM used by Arazo, it used the mix match that was proposed 2 years ago, and they combine everything together. And by combining everything, by combining co-teaching, on data augmentation, and with the semi-supervised solution, it improved a lot the state of the art. And it basically says that if you want to have the top results, the best way is to combine ensembling approach, data augmentation, and semi-supervised solutions. So the divide mix method trained two models simultaneously, and for each model, it will calculate the Gaussian mix model to have the probabilities of a sample being clean or noisy. And the filtered samples will be sent to the other network. After that, they use the mix match algorithm to combine the clean samples from one model with the noisy samples from the other and update the model. The algorithm seems complex and extensive, but it's just the mix match algorithm combined with co-teaching. And as we can see by the results, divide mix improved a lot the results mainly on high noise rates, such as 90%, where the previous state of the art was 69 for CIFAR 10 and 24 for CIFAR 100, and it improved more than almost 10%. For the large-scale datasets, such as Clothing 1M and Web Vision, it also improved the results. So the general idea of the state-of-the-art models is that they show that using data augmentation, it's useful for combating noisy labels. Assembled methods are also important to combat noisy labels. And the best solutions are those that somehow they use the noisy samples to help in the training. So instead of just filtering the clean samples, it's more useful to try to combine, to use the noisy samples can by either by combinations of clean and noisy samples, or by using some regularization laws on the noisy samples, but using somehow the information for the noisy samples to help to train the model.
Right.
Nice.
That was very, very interesting. Thanks for that. I was just having a look at the chat and realized that I guess I'm the only one who actually posted technical comments or questions there, and one of them was exactly about the mix-up, which you ended up talking about it later, which I thought was very nice, and I must definitely agree with you that the simple techniques are really the most interesting. I mean, my favorite ones. So mix up is one of them, and then the other one about the negative training, right?
The negative training, people are not using that much, but mix up, all recent papers they are using It's like a standard data augmentation nowadays, because it's really simple, it's easy to adapt, and it really works.
Yeah, and it's interesting that. So yeah, I mentioned it because I actually saw it as part of the Fast AI tutorial, right? The Fast book by Jeremy Howard and others, and he talks about it just as a way to make your method more robust. I mean, he's not he didn't even mention it as in the context of, well, maybe he did, right? But the main purpose was really getting better performance. Right?
In the paper, they have an evaluation for noisy labels, and they show that it improves.
Yeah, I think, well, the other thing I mentioned was like some old piece of work by the team from the University of Surrey with Joseph Kittler and others on domain anomaly detection, which is a paper that came out in 2014, but obviously at PAMI, right? But most of the work was done back in 2012, so definitely before the whole deep learning wave even started to when it was about to start climbing. So it ends up being a bit different, and he actually talks more about the different ways of setting up, well, describing anomaly in terms of domains and so on. So it's not that much about
there are some approaches that try to view the noisy label problems in a perspective of anomaly detection. So I didn't show in these related works, but a few years ago that there were some papers that tried some anomaly detection methods applied to noisy labels, and they seem to work well to identify types of noise. But in general, you can look at a sample as noise if most of the sample, you can look at it as an anomaly if most of the samples are clean. If most of the samples are noisy, that's not an anomaly. Anomaly will be the clean samples. So that doesn't work.
Yeah, that makes sense. And I think there's a lot of work recently. I mean, okay, before there was a lot of work on domain adaptation. There is still a lot going on about that, which I think is a sort of related problem, except that it's not a problem of having noise, but actually having a whole data set shifting towards a different domain. But when you look at the techniques that actually try to design methods that have more domain, well, generalization, right? That are more robust or domain agnostic methods. Essentially, they try to make their methods more robust by modeling noise, and I think it's quite related to this kind of area. So when you showed that slide showing papers about dealing with label noise and so on, I thought, okay, even though you clearly state that this is about number of papers in this subject that were published in the main AI conferences, I think there's a lot of terms which are, I mean, there's a lot of work that is somewhat related, but they might use different labels, and maybe the whole idea of domain generalization might be quite related to this, I guess. I don't know if that included it.
No, for sure it's related, but I haven't seen many works doing this link between domain generalization, domain adaptation to noisy labels, mainly on these big conference like CVPR, NIPS. So I think it's an interesting way to follow, and maybe we could have some good results, but I think most of people haven't looked at noisy label problems in this domain generalization perspective. So I think it's also related and it's interesting, but that's not the way that people are going right now.
Okay, yeah, that makes sense. All right, I don't know if you have any other comment you would like to bring now that you saw your own video. You might want to mention something.
So I can talk about the link to the GitHub that we will use in the next after the break, right? So we have all the code that we are going to use in the next video after the break, that we have the link on the screen. That's on my GitHub. So you can have access to it and open it will open a Google Colab page. So I will run all the code and explain right after the break.
Excellent. So we're going to be back at 4:15 in Brazil's time. So yeah, in just under 20 minutes. Okay. Right. See you soon.
Yeah.
Hello. Hi everyone. Welcome back to SIBGRAPI tutorial 2. We're gonna start the third part of it, the third and fourth part are the practice, I believe, right? So
Yeah, that's right.
It's gonna be run using the code, which is linked, whose link is shown on the screen. And just before giving the word back to Fabio and then bringing the video again, I thought I should say some acknowledgements before I forget. If I leave it to the end, I might forget. So I'd like to thank Saskia Grunwegen, who prompted to be a co-chair of the workshops. She couldn't attend it and be a chair in the live session because she's in the Netherlands. Her time zone is not ideal for this at the moment, and also because actually the main reason is she's way too busy organizing the Global XR Bootcamp, a massive event on mixed reality, which is going to start next week. So yeah, she's from Ordina, a Dutch company, and she actually mobilized quite a few of her colleagues in her network of collaborators to help with reviewing proposals for this the tutorials. And I would also like to thank Lindeberg Pessoa Leite, who is a PhD student here at the University of Brasilia, and he prompted. He he was volunteered to take Saskia place and be the chair of tutorial 1 right now. So yeah, I'm very grateful for him to step up and get this done, even though I gave him such a short notice. Yeah. Anyway, so I guess I can give the word back to Felipe, and we can proceed. Felipe, you want to say anything?
Yeah, thank you very much. Now we start the third part of the tutorial. That's the practical part where I will show some code. I'll show what I want to show is that although I have showed many different techniques that they might seem a little complicated to understand or to implement, my goal here is just to show some simple solutions, how you can have in your own data set and have in your own method, just to try some simple solutions that can help your model to be more robust to noisy labels. So in this activity, I'll show some code. It's on PyTorch. If you don't have, if you have never worked with PyTorch, don't worry, because it's very similar to Python. It's easy to understand, and in the video, I'll explain all the code, and you can run all the examples that I'm showing. Just have access to the GitHub. You can find the code and the slides. And if you have any questions, you can just ask, and I can explain everything. So I hope you enjoy, and you can reproduce all the results that I'm showing.
And there's a link. When you open the code page, the first thing you see is a link that lets you open it straight, directly on Google Colab, so you can actually try it live as the course goes on. Right?
Yeah, and yeah, I will show that on the video. And for some experiments, it will take maybe 1 minute or two to run, and I won't speed up anything. I'll just show in real time, like when I recorded the video, so you can have the same results. That do everything simultaneously if you'd like to do. So I hope you enjoy it.
Okay. Let's go.
Hello everyone, this is the practical activity of the tutorial where I'll show some code and run it on Google Colab. So I have published a code on GitHub where you can download using this link. It's github.com/philippe-research/tutorial_noisy labels. There you find a code that you can open on Google Colab, and you can run some examples. To access the code, you can open the codes folder and then click on tutorials SIBGRAPI with this extension that is from Jupyter Notebook. When you open it, you see the code. There is no output because I want to run in real time, and there's a few things to show you the outputs, and we can discuss about strategies and the noise, the types of noise. So the idea is that you can open the code using Google Colab. Just by clicking this link, it will open a new tab. So this is Google Colab. Google Colab is a service from Google where you can run codes in different languages and run on Jupyter Notebook. So everything is in the structure of Jupyter Notebook, and they provide access to GPU and TPU. So the idea is that to run the code, you should go here. This is in Portuguese, should be in English, but it should go to here, set up notebook, and then you can find the option to use GPU or TPU. If you don't choose anything, it will run on CPU and it will be a little bit slower. So I will select GPU and save. So for this tutorial, the idea is to run a simple example where we can train the models and in a way that it doesn't take too long to finish, because I want to show a few examples, and I'd like to give the opportunity to you run the code at the same time, and therefore I won't cut anything. I won't do any video editing when running the examples, so you can follow in real time what's happening, and if you have any questions, you can ask. The dataset that we are going to use is the MNIST dataset. It's a classic dataset for image classification, and it's a dataset of numbers from 0 to 9, and it consists of 60,000 images for training and 10,000 images for tests. The state of the art for this dataset is very high. It's around 99%, and it's very easy to have high results using very simple models. So it's just like a hello world for image classification context. So with any kind of classifier using an MLP or a simple classifier, you can easily get 97, 98, or 99. But here we are not focusing on getting beating state of the art or getting 99% accuracy. We just want to show how can we get better results when we have noisy labels in our dataset. One important thing is that on MNIST dataset, we won't find any kind of noisy labels, or maybe just a few images, but the percentage of noisy labels that we can find is irrelevant. So we will use this data set, and we will add synthetic noise to it. We will add symmetric noise and asymmetric noise, and then we will run a simple model with different noise rates and propose some methods to improve the results with the noisy labels. So I will explain each part of the code. All the code is in PyTorch, and the PyTorch is very used in academic community. The biggest conference when they publish code, they usually publish either on PyTorch or TensorFlow. In the last years, much more on PyTorch. So I have started to use PyTorch in the last years, and it's very easy to find noisy label solutions in PyTorch as well. So I would heavily recommend to, if you don't know PyTorch, to have a look later and try to run some codes. The syntax is very close to Python, so if you know Python, it will be very easy to adapt to PyTorch. One of the problems that I had with PyTorch and Google Colab is that I found it a little bit slow when running codes with PyTorch. I used to run codes with Keras to run CIFAR, MNIST, and medium data sets. And with Keras, that's another library for deep learning, I found it that's much faster running on Google Colab. But running on my local machine, PyTorch seems to be a little bit faster. But I don't know what happens with Google Colab. And I tried to solve it, tried to make it faster, but I couldn't solve this. So when we run the models here in the tutorial, it will be a little bit slower. It will take maybe 2 or 3 minutes to run each experiment. So I ask you a little bit of patience to run everything. But we'll be talking and discussing about the topic, so it won't be so bad. So the first part here, I'm just importing the dependencies, the Torch libraries, the matplotlib, scikit-learn libraries, just regular libraries that we need for Torch and Python in general. Then we define some hyperparameters. I needed to use a small training size of 2000 samples, just because otherwise it would take too long to run everything. Even if it would take like just 10 minutes to run one experiment, it would be too long for the tutorial. So a way to run fast in a presentation is to reduce the training size. And that's why I'm reducing to 2000 samples. The MNIST dataset, it has 6000 samples for training. And usually if you have a good GPU, it would take just a few minutes to run, maybe 5 minutes. But on Google Colab, it's like a little bit slow. As I said, that's why I needed to reduce the training size. And also I'm just using 50 epochs, but usually when you train a deep learning model, you use more epochs like 300, 500. And here we define the batch size equals to 128, the learning rate, and the seed just to every time that we train a new model, it starts with the same initialization. Here we define some initialization for Torch and the random library. And this part here is a PyTorch code to say if you are using a GPU or a CPU. So to run a cell in PyTorch, on Google Colab, you can just press Shift Enter. You can press OK here, just because it was from GitHub. And it will run the first cell. The first time it takes just a few seconds, but it's normal. You can also run pressing, through the tabs, but you can just press Shift Enter. You can also have access to all the sections that I've made for this code and just jump to another one, but we will see this later. So I run the first cell, it has the number 1 here, and then the second cell, just to set the initial parameters. So if it shows here that shows CUDA means that you are using CUDA, otherwise you are running the CPU. Okay, so I need to download the MNIST. If you don't have MNIST in your machine, there's not a problem. You can just download from the library. So this is just a standard code for downloading MNIST dataset. I'm saying that I'll do just a normalization. I won't do any kind of data augmentation like flip, rotation, or anything else. I'm just downloading the training set. I'll save here as training data, and then I'll download the test set and save here as test data. And these are commonly used normalization parameters for MNIST. If you'd like to add some kind of normalization, some kind of transformation, you would just add a new transformation here. I don't remember. Yeah, they have random crop, they have rotation, they have some operation that you can add, and that's very easy to do with PyTorch. So Shift Enter, it will start to download it. Okay, it's downloaded. You can check that it's here. Actually, in this folder here, you see on data, you have the MNIST. So it's everything here. So when I downloaded the training set and the test set, it downloaded the full data set. So the training set has 6,000 images, but I want to use just 2,000 just to make it quicker. So on my training data, I have access to the data, and I will limit the size to the training, my training size, that is 2,000. So it will get all the images from the first one onto 2,000, and it will save here. And I'll do the same thing for the targets. So the first line, it reduced the size for the image, and second line, it reduced the targets, because this is a vector here. So for example, if I show this, it's a tensor array. So we can check, for example, the shape, and it has 60,000 because I didn't run the cell. But after I run it, it will have 2,000. Okay, and same thing for data. Sorry. The same thing. Okay, the images from MNIST, they have the size 28 by 28. And next, I will generate a data loader, because on PyTorch you first download the data, or you load the data, and then you build the data loader that during the training it will pick the batch size and do the transformations and everything. So here I'm generating a data loader that will receive this train data that has 2,000 images. I'm using a batch size of, I forgot, batch size of 428, and I'm shuffling during, I want to shuffle during the training, so my data loader will have that. And these are just a few parameters for the, how you load your data from your computer. So I have the train data loader. I have the test data loader. Usually that's the only things that you need But I also will need an evaluation data loader just because of an algorithm that I'll try that use mixture of Gaussians. So it's just another data loader. It will use the same training data, but the difference is that I don't want it to shuffle the samples because I need to keep track on all the samples. And for my code, I need to have access to the samples by the index. There are some other ways to do that. Some easier ways, just like creating a data loader class, and maybe you'll find an easier way to do. But this is just because of a code that I'll show that I'll need that. I'll talk about that later. But when you generally when you use the MNIs, just the train loader and test loader. So I need to run this cell. Okay, you can do the same if you are running now as well. And I'll plot a few images from the data set. So here I'm just taking a batch from. Actually, I'm picking a batch from the test loader, and I'll show just a few examples from the data set. So this is how the image look like. These are the ground truth labels that we can call the true labels or the hidden labels. These we won't have access. Now we have access because we are using a clean data set, but we will add synthetic noise to it, and it will be more interesting when everything is wrong and you have to train your model. This one looks like an 8, but it's a 5. And everything else looks fine. So after that, I will define a network that I'm using. So I decided to use a very small network, a convolutional. It's a convolutional neural network. It has 2 convolutional layers and then 2 fully connected layers. And this is a very small architecture just to run everything fast. But you could use any architecture. Usually what people use to work with noisy labels is the pre-activation ResNet 18. I will add this comment here. Usually people use React ResNet 18. Or some variation like 50 or 101. But you could use any one. But if you want to compare to state of the art, you'll find more papers using this kind of architecture just because other people started using, and it's easier to compare if you use the same architecture. So that's good because this architecture is not very heavy and doesn't take much time to run. So I recommend using this architecture. So I need to run the cell as well to have access to this class. And then I'm defining the cross entropy. This is from the PyTorch library. It's just defining, initializing the class cross entropy that will calculate the cross entropy. And when we use PyTorch, we have to send some things to run on GPU if you decided to run things on GPU. As most of the times we want to run things on GPU, you have to use these 2 device, or you have other options that if you know that you want to use GPU anyway, you could just use like .CUDA instead of to device, because I defined that this device depends on if the GPU is available or not. Like here in the beginning, the very beginning, inside the device can be either CUDA or CPU, depending if it's available or not. So what do you usually need to send to device? You need to send your model that I'll send later, and you need to send the image and the labels, but I'll show later. I'm not sure if you need to send the laws to device. Actually, I didn't check without using, but usually I always put, because it doesn't show any error when I use like this. I'll just let the other comment. Okay, so in PyTorch library, they have available different types of laws just to call the type of laws that you want to use, and you can build your own losses as well. So it's very easy to use. One thing that I like about PyTorch is that it allows you to do many kinds of things and to modify the models as you wish. So when using carriers, you don't have much access to create something very new, very unique, and you have a few restrictions that on PyTorch you don't have. And TensorFlow as well, it has you have a lot of access to do many things, but TensorFlow is a little bit more complicated, and PyTorch, as it is very similar to Python, it's very easy to start using it. Okay, so I'm running this cell as well. Okay, if it has a number, it's because you run it. And then I'll define my test method and my training method. So this is a default test method. I won't talk much about it. Maybe it might be difficult just because of PyTorch syntax, but this is what I'm using here is that I'm using for to get a batch every time, every iteration of the for, and then I'll do that I said that I need to send the data, that's the image, to the device, that in case is my GPU, and the target to my device as well. And then I will have my network that I will receive as a parameter, and I'll give as input my data, and it will give the output. Okay. Something interesting is that this output is not the result of softmax. Actually, when I defined my network, the output is the outputs are the logits of the network, and that's why that's because this cross entropy loss, it's expecting the logits and not the softmax. Into the cross entropy loss function from this class here, it will call the softmax. So in this type of coding, you send the logits to the loss function. So here I'm sending the logits and the target, that are the labels, and then it will calculate how much it's correct. Then it will return the accuracy and the test loss. And then I defined an evaluate method. I won't talk about this right now. I'll talk about later, because in the beginning I won't use this very much. So I'll skip that for now. I'll come back to this later. And then I defined the train epoch. For the train epoch, the idea is to run all the batches and calculate the train accuracy and loss and update the model. So when we run a model on PyTorch, we need to say if it's training or not. For example, on the other code, we had net.eval. That means that it won't calculate gradients for the operations. So it won't modify anything in the weights of the network. And when using train, I wanted to calculate the gradients and to save the gradients and do the modifications after I calculate the loss. So that's why I run net.train every time before training. So here it will get a badge for every iteration, and then I get the image and the labels, and I'll send to the device, that's my GPU. I initialize my optimizer, and then I send as input my batch of image and get my logits. Then I use my loss function that I will receive, that will be the cross entropy, send the logits and the labels, and then calculate the loss. Here I'm saving the loss, but when I do loss.backward, it will calculate it will do the back propagation and update the weights. Everything is done here. All the update of the model is done here. And then I reset, actually here it calculates everything when I use loss.backward. So I don't need to calculate in derivative or anything else. It just do everything automatically. And so after this, it will have calculated the gradients. And when I use optimizer.step, it will update the weights of the model. So in the end, it calculates the accuracy and loss, calculates the average of the loss, and return. And I defined another method, that's train test model, that it will call the train epoch model at every epoch. And in the end, it will call the test method to save the results. So here in the beginning, it will initialize the network and send it to the device, that is the GPU, and initialize my optimizer. I'm using Adam optimizer with the learning rate that we defined previously. Here I'm initializing a dictionary where I'll save all the logs, and the loop here is basically to train the model epoch, save the logs, append the results to my vector, and then call the test method. And in the end of each epoch, I print the results. Okay, if you have any questions about PyTorch syntax, you can ask anytime. Okay, so this is just the setup and explanation of the code for training test. And now what we need to do is to run a baseline of the clean data set to see what's the best that we can achieve with this model and with this amount of data. And then we will add some noise. And after adding some noise, we will see how much the accuracy drops, how much the noise labels, the impact on the accuracy. So here in this line, I'm calling that train test model, and I'm saying that I'm using the cross entropy loss that I defined. So I pressed Shift Enter, and it should start running. Okay, maybe I didn't run the cell from testing. Yeah, it is empty. It doesn't have a number. Okay. So I'll go back there and run again. Okay, it's running. So we have here the train loss, the train accuracy, the test loss, and the test accuracy. And it will run for 50 epochs. So as we are running with a small training set, like we are using 2,000 samples instead of 60,000, you might not get that top results like 99% because of these two reasons. First one is the training set that's small, and second one is our model that is a very simple model with only 2 convolutional layers. But if we use some state-of-the-art model, or maybe a simple model but just with a few more layers, or maybe change the parameters and use the full data set, so we can easily get 98 or 99 without any problems. Because the MNIST datasets is the easiest dataset for image classification, as for my knowledge, and you don't have to do many effort to achieve high accuracy. So it's just to test, just to evaluate. So we are getting 95. That's kind of impressive because we are using only 2,000 images. Okay. We might not get more than 97. Just 10 epochs are to finish. 95. Have to wait a little bit. Okay, you see that for the clean set, the train accuracy is quite high, but when we use noisy labels, it drops a lot. Okay, so it finished. It's 50 epochs, but it started from 0, so it goes until 49. And okay, so I'll plot the results for this training. So this code will plot the training accuracy, test accuracy for, yeah, the accuracy and loss for training and test sets. So these are the results. The test accuracy, it increases over time and has a convergence around epoch 30, and the training does the same as well. So it seems pretty good. It seems a normal training with fast convergence and the loss dropping in a few epochs. It's everything fine, beautiful, no problems, high accuracy in just a few epochs with a small training set. So we just have to memorize this number. Our test accuracy is 95. That's the maximum that we can get using a clean data set. So we won't use clean data sets anymore. So now we are going to add some noise to MNIST dataset. Okay, so the first thing that I need to do is to save the clean labels, just to reset my dataset and to have access to clean labels, just to comparison, because in some point I need to check the noise rate and need to check how is the behavior of the clean samples and the noisy samples, just for tracking. I won't have access to the clean labels for the training itself. The model doesn't have any access to the clean labels, just to the noisy labels. So I'm here I'm saving the targets. I'm cloning the targets and saving here on the ground truth labels. So I'm saving it here. And I have here a code to generate all my noise. So I defined here a transition dictionary. This transition dictionary is to generate my asymmetric noise. So the asymmetric noise, it is predefined. So what it says here is that if I have a label 0, it will be mapped to 0, so there's no changing. If I have a label from class 2, it will be flipped to 0, 4 to 7, 7 doesn't change, 1 doesn't change. So, oops. 9, it's mapped to 1, 3 to 5, 5 to 3, and the other doesn't change. So, for example, if I define a noise rate of 50%, and what it means that 50% of the labels that of the samples that have label 4 will be flipped to 7. 50% of the labels, the samples with label 9, will be flipped to 1. Okay? So this is exactly one of the transition matrix that people use for M&Es with asymmetric noise. And here in this method, I define how I generate my mode, how I generate my noise. So I receive as parameter the noise rate, the ground truth labels, and what type of noise I'm going to use, if symmetric or asymmetric. So first I'll shuffle all my ground truth labels just to make it more random. Sorry, here I shuffle. And then I will calculate how much noise I'll have. So I'll get the amount of labels that I have multiplied by the noise rate. Okay, so this will return the amount of samples with noise. And then I'll get the index for the noisy samples. So if I have 1000 image with noise, I'll get the first 1000 index. Because it's shuffled, it doesn't matter. So I will loop for every label that I have on ground truth labels. And if it's symmetric noise, I'll just do a random flip. This part here is important because when I have a sample that its label will flip, it can be flipped randomly from 0 to 9. So for example, if its label is 2, it will randomly flip from 0 to 9. So that means that 2 is also included here. So it has a chance of 10% of maintaining the same label that it was before, that it had before. This is the most used type of symmetric noise, but a few authors, they prefer not including the original label between the possible flipping labels. But most of the papers, they use this strategy of randomly flipping, and you can randomly flip to the same label that you had, so it will not generate any change. But that's how people do, so we are following the same strategy. And here we have the asymmetric noise. The asymmetric noise, we are just following this transition matrix here, and it will flip according to the matrix. So in the end here, it will return all the noisy labels. Okay, so I'll run this cell.
Speaking of noise, there's a bit of noise here. Yeah, anyway, we thought this was a nice time to have a pause. So it just shown how to, define the function to generate noisy labels, and so on. And he's gonna later plot some samples and noise. So if anyone wants, who is following the code.
The general idea is that we are going to generate some noise, and run our baseline to see how it behaves. And then we will add some losses that are robust to noise and other strategy to see how much you can increase our results with the noise environment. So this first part, I needed to explain how was the training and test and how to generate the noise, just to make everything clear if anyone is not familiar with the PyTorch syntax. But after the break, we'll see more about the results with the noisy labels and then some solutions that you can easily adapt to your own algorithms.
Yeah, I thought it was very nice the way you introduced this. Like, so for most of the last 45 minutes, you actually gave a PyTorch tutorial, which is very interesting because I think most students are actually more familiar with Keras and TensorFlow, right? So it was very nice that you showed that. And I think it's very nice and clear. And now we're actually getting into the main subject.
Yeah, and it's good because everyone can see how close it is to Python syntax. So you don't need to be afraid of using PyTorch because it's not that hard.
Exactly. I think if you're a Python programmer, using PyTorch is definitely, the learning curve is less sharp than going to I guess.
And it's what people are using, like when they publish paper and they publish code. So if you want to reproduce results, you have access to PyTorch code. So you won't find like big conference publishing code in Keras. So it's easier if you just start using PyTorch. So it's easier to reproduce other codes and to compare later, and it's easy to run, and you can see by the code. And if anyone has any questions about PyTorch or about the code, you can send me an email later or just ask here during the chat, and I can answer.
Yeah, I think this whole discussion about TensorFlow versus PyTorch can take a while.
Yeah, sure.
But I think maybe it was a little bit like the US election vote counting. PyTorch was definitely a lot more popular in all machine learning conferences and computer vision, and actually TensorFlow was more popular. Sorry, and then I believe about 2 years ago we could see this flip, which was about when TensorFlow 2 got released, and I think it didn't actually. I guess TensorFlow 2 didn't actually stop this thing about PyTorch attracting more people, at least in terms of researchers. But obviously, all Google papers tend to do things in TensorFlow because they actually maintain it. And you also mentioned that running PyTorch code in Colab is a lot slower than TensorFlow.
Yeah.
But there might be a reason for that, right? They actually own TensorFlow, so they probably do the best they can to.
For sure, if you run a TensorFlow code, it will be much faster.
Yeah, but I agree. If in terms of running on your own server, your own machine, I think the anecdotal report that I hear is that PyTorch tends to converge a little bit faster in the training. Even I think. Well, I'm gonna mention the Fast AI tutorial again because he actually at some point, I think in an earlier version of the tutorial, he actually compared the two frameworks for the same architecture, but this was actually with TensorFlow 1, and back then PyTorch was much faster to get to the same results. But I think now things might have changed.
Yeah. In general, the community have a lot of respect for TensorFlow, and I think nowadays TensorFlow is more used in the industry, while PyTorch is for academic research. The good part of PyTorch, it's that it's more user-friendly, so new student can easily learn it. The learning curve it's better for PyTorch. So my only complaint was about Keras, because Keras, although it's very good for people who are starting with deep learning and are starting to do the first projects, like students from the university, it's very easy to run your things, but it doesn't allow much access to build your revolutionary algorithm with different architecture, and that's easier for TensorFlow and PyTorch. That's why people use more TensorFlow and PyTorch on for top research, high-level research. So both are good. Just PyTorch, TensorFlow is a little bit more complicated to debug, mainly for debugging, and if you are just starting, it's harder to understand other people's code. While for PyTorch, if you know Python, you can easily read the code and have an idea how it works.
Yeah, and just I would mention that in TensorFlow 2, as I understand, Keras got sort of assimilated into the framework, right? So I guess we don't really distinguish between Keras and TensorFlow anymore, I guess. I don't know. But in terms of industry versus academic institutions, of course, it depends on the industry, right? If you actually work for Facebook, you definitely use PyTorch, right? Because I think they're the main maintainers, or maybe the only. But anyway.
And if you do research for Google, you work with TensorFlow.
Of course, yeah. Okay, I guess we can have a break now. Well, we had a little bit of discussion, so we'll be back in about 7 minutes. Yeah, 5:15, and carry on with this video. All right, see you soon.
See you.
Pode falar, Felipe.
Okay. So in the last video, I just started running the code for the baseline that I just wanted to have an idea what's the accuracy that we have for a clean data set that was around 95%. And now we are adding synthetic noise to our data set, and we'll see now how it behaves with noisy labels. And in the end, we'll add some solution to get more robust results.
Okay, we can carry on with the video.
And here on the next cell, what I do is I'm kind of generating a benchmark of noisy data sets, and I'm running, actually, I'm generating data set with 50% symmetric noise, 70% symmetric noise, and 40% asymmetric noise. Just because I'll need to have access to it several times, so I'm saving here separately, so we can access later. So I press here, Shift Enter, and it's already generated. And one thing that I want to show is that when we define, for example, let's say 50% symmetric noise. So what you can expect is that the noise rate that you have, it's really 50% noise rate. But that's not what happens. For example, here, I'll just print the noise rate for 50%. So here what it's doing, it's comparing the labels from this data set that I just generated, the label noise with 50% symmetric noise, with those my ground truth labels. So it will calculate the amount of noise that all the different samples, the number of different samples divided by the total of samples. Sorry, the number of different labels divided by the total of labels. So what we have here is that for 50%, the real noise is 45. But why does it happen? Because we have 2,000 images, and for these 2,000 images, we had a noise of 50%. But remember that here, the asymmetric noise, it has 10% of chance of keeping the same label. So it has 90% of chance of flipping to a different label. So it's this number times 0.9. Sorry, this is the amount of samples that we have. So this divided by 2,000. It will be 45%. Okay, so for 70% symmetric noise, we'll have 63%. Okay, that's the same idea. And for asymmetric noise, how much it will have? It has actually 20% real noise. So why does it happen for asymmetric? Because in the asymmetric noise, if you count here, we have the labels that really flip are 1, 2, 3, 4, 5. So we have 40% noise, but only 50% of my samples, if my data set is balanced, only 50% of it will have noise. They will flip labels. So it's 50% of 40%. These things that I'm saying, people don't talk on the papers, but it's something that everyone knows, but nobody likes to talk about it. Because we define a noise, but the real noise that we have on the data set is not that. So 70% noise, we can see on the papers 70% noise, but the real noise it's 63. So it's always a little bit lower. Okay, so I generate the noise, and I'll plot some images of the data set. In this case, I'm using this 70% symmetric noise, just to show how they look like. So this is some samples of the data set for 70% symmetric noise, and we have this situation, have an 8, but our label is 2, 4, but the label is 2, this one is correct, this one's correct, 5 label is 1, 9 label is 0. So this is how we are going to train our model, giving this kind of information. So we'll give a lot of wrong information to our model, and we want it to learn everything, even having wrong information for most of the samples. So how that's possible? Well, you can teach the model how to identify what is clean and what's noise, and learn only with the clean samples, or even learn as well with the noisy samples. So what I want to show now is how this data set looks like, just to show more examples. So I want to show the transition matrix, actually the transition matrix generated by the symmetric noise with 70% noise rate. So here I'm just calculating how many times the labels are different for each class. And then here it's just a code to generate a table, a transition matrix. It will generate actually it's like a confusion matrix. So here we have that transition matrix with noisy labels and true labels, and we have the original class and the noisy class. So here, for example, if we have a true label 4, it has 35% probability to change to a noise, actually to keep with that label. And it has, for example, 0.8%, 0.9% chance of flipping to class 2. So we can say that the probability of our observer label be equal to 2, given the hidden true label, I'll call like this, equal to 4. This is just to do some math. This is equal to 0.089. Okay, that's something like that. In our symmetric noise, we expect that the probability of the observed label have the same class as the true label be the same for all the classes. So we expect this diagonal should be the same for everyone. Here it's close. It's not exactly the same, but that's because the data set's a little bit imbalanced when I reduced the training size, and I was not worried about guaranteeing that all the class would have the same amount of opportunities to flip their labels. So here I'll show this code here. I'll just show how imbalanced the class is, the data set is. This is with the noisy data set. So it's a little bit imbalanced. That's why we can see this difference. And if we look to the original with the ground truth labels, we would have like this. So it's imbalanced, and that's why you have this difference here. Okay. And if we look for the asymmetric noise that we have for asymmetric, I'll just show the transition matrix. You see, so the transition happens just to a few classes, and all the other classes like 4 to 6 or 4 to 9, it has 0 probability. So it is as we define it here. Here, no, sorry. Here, okay. So it has this behavior. Okay, now we have generated the synthetic noise. We have our baseline that was training with the clean data set. And now we run our model with the noisy data sets. So I'm running first for 50% with that cross entropy. Okay, it will take a little bit to finish. And I want to run the experiments with 50% symmetric noise, then 70%, and then 40%. And I want to show the results for the training accuracy, training test accuracy, the loss for the training, and the loss of the test. So you can see how different it is from when you train with a clean data set and when you train with the noise data set. Here you can already see that the training accuracy it's much lower than when we trained with the when we trained with the clean data set. And when we trained with the clean data set, we were expecting here, actually in the end we had 97. Let me check, I forgot. We had, yeah, 95 actually. So with everything clean, we got 95. How much we can get with 50% noise rate? So it's in 91. Maybe it won't increase much. Probably to 93, 92. One common thing when training with noisy labels is that usually you have the best results during the first stages of the training, and after training a few epochs, the model starts to overfit. So it's very common to have a strong overfit when training for long periods. So here, for example, it was 91 and it's decreasing to 90 and came back to 91. Okay, so this one finished. This one was 50%. This one actually hits 70%. I'll run the same thing, but for 70% noise rate. I have all the logs saved here. They are saving for 50%. And now for 70%. Usually on the state of the art, people have used very high noise rates to evaluate the models. The paper from state of the art, they evaluate their models until with 90% noise rate, and that's a very high noise rate. And it's still having 90% noise rate. Actually, the real noise rate is around 82, something like that. But it's very impressive to train a model with 90% of labels wrong and still have a pretty good result that's close to training your model with no noisy labels. That's very impressive. But this for symmetric noise. The symmetric noise is the easier type of noise. So people have found out a few tricks to how to identify the noisy samples when you have symmetric noise. Unfortunately, that's not very realistic to train a model, to find data sets with symmetric noise. But to have a solution for more difficult noise, you have to evaluate your model for symmetric noise. And in general, if it works well for asymmetric noise, for example, it will work well for symmetric noise. So here we are training for 70% noise rate, and you can see that the results are much worse, at least until now. The training accuracy, it's around 31%. Our test accuracy, it's 84, 85. The accuracy for the clean data set was 95, so you can see a drop of more than 10%. But here we have a very high noise rate of 70%. Okay, so this one finished. And now I'll run this one, that's the last one for the baseline, and the asymmetric noise. The asymmetric noise, for 40% asymmetric noise, it's a little bit easier than 70% asymmetric noise. So with asymmetric noise, the maximum noise rate that we can have, it's 49. Otherwise, we can't do the training, because we need to have at least more clean samples than noisy samples from one label. Otherwise, we can't identify that label. And if you have more classes without data set, it's also more difficult. So for example, the CIFAR 100, that's another commonly used data set. The results for high noise rate and asymmetric noise, they are very low. Like for CIFAR 100 with 80% noise rate or 90% of noise rate, the state-of-the-art achieves 30%. The same state-of-the-art that can achieve 90% with CIFAR 10, 90% noise rate, it achieves 30% for CIFAR 100. So it's still an open problem to work with a large number of classes and to work with very large data sets. You can see from these results here that although the test accuracy is a little bit lower, the train accuracy is much higher than the other noise types that we run. That's why on asymmetric noise we have a lot of classes that didn't change the label, that doesn't have any flipping. So in this case, for the transition matrix that you use, only 50% of the classes flipped the label. So that's why we can have a high train accuracy, because many of the samples are with correct labels. And this data set as well, the real noise that we have, it's around 20%. So this one has finished. And we'll plot now the results for everything. So this code here is just to plot. You don't need to worry about. It's just for plotting. So here I press Shift Enter, and it will show the results. So we have these beautiful plots here. I'll start with this one. This shows the accuracy for training and test. The training is this dashed line. So the training of the clean data set, it's pretty high, the accuracy. And as I increase the noise rate, as I add noise, it dropped to this is the 40% asymmetric in blue. The red is the 50% symmetric, and the green one, that's the lower one, it is 70% symmetric. And when we look to the test accuracy, we can see, I'll just remove this to make it easier to read. Just see. Just comment here. Okay, a little bit better. I'll just limit the range here to help the visualization. 0 to actually. Okay, so we had the test accuracy around for clean data set around 95. For 50% symmetric, it dropped 5% almost, and the asymmetry and 70% symmetry and the asymmetric noise, they dropped a lot. So compared to the clean set, they dropped more than 10%. And looking to the loss, you can see that the more that you increase the noise, that you have noise in your data set, the more difficult it is to the model to fit to the samples. Okay, so we have evaluated how bad it is to add noise to your data and how it affects the accuracy and the convergence of the model. So what we want to do now is to test some solutions to try to improve these results a little bit. So the simplest thing that you can do if you have a model and you have a noisy data set is to use some robust loss, because robust losses are very, very easy to implement, to add to your model. And there are a couple of available code that you can easily use. So for example, here, I'm using the code from the paper that they show. They propose an active passive loss, and they provide the GitHub code. The code is on PyTorch, but it's very easy to use. And here on the tutorial code, I also am defining some of that losses that we are going to try. I think we are not using all of them, but I just tested them. And it's basically the cross entropy, that's the normalized cross entropy. They have the reverse cross entropy. That's just the cross entropy, but swapping the prediction and the targets in the cross entropy. We also have this is the one that will combine the normalized cross entropy and the reverse cross entropy. And in the active passive loss, they need a parameter alpha and beta that they will give weight to the active loss and the passive loss. So I'm pressing Shift Enter to all of them. And I think this one I'm not using, but in their paper they also use normalized focal loss, and they also test the combination with normalized focal loss and reverse cross entropy. And finally, they define the mean absolute error, and there's definition of normalized cross entropy and mean absolute error. So this is just to show that it's easy to use the losses on your code. There are a lot of robust losses available, and you can easily adapt. So what I would do, as training, everything takes a little bit of time. I would just train for 70% symmetric noise. That's the most challenging. And I'm saying here that I'm gonna use the normalized cross entropy and the mean absolute error, and I'll use a parameter alpha equal to 1 and beta equals to 1. In their paper, they don't use that. I'll show what they use. So in their paper, they say here that in the parameter setting, that they also try for MNIST dataset, and with their APL loss, they use an alpha equals to 1 and beta alpha equals to 1 and beta equals to 100. and they show in the results that using this one, they have good results for MNIST. And I tried these values of 100 and alpha equal to 1 and beta equal to 100, but it didn't work well. And I tried other parameters, and the one that I found that worked better was using beta equals to 1. This might happen because we are using a different setup for MNIST. We are using MNIST with only 2000 images and using a different model. And this is a kind of annoying and tricky thing that you might find when trying to use models in general, deep learning models in general, and mainly these ones that have regularization and have weights, because sometimes it's not just to use the paper that they provide in their papers. You have to optimize your problem, and sometimes it's not easy. And in this case here, I had to find another parameters. Maybe you can try different parameters and have better results, but I tried to use the ones from the paper, and I had some problems when running it, and then I decided to do a few tests, and I found this one that worked better. So I'll just run here. I'll be running for 70% symmetric noise, and yeah, and then we will compare the results with our baseline. Actually, we have the baseline for the clean data set, and we have the baseline with the noise data set without any kind of robust loss, just cross entropy, and we'll see how much it improved the results. Another problem that you might find is if your data set is too small, maybe these solutions that I'm showing, they can behave a little bit different, because most of the solutions, they are proposed for large data sets, like you have 50,000 images, you have 100 images. There are not many papers that focus on small loss, because usually researchers use only those classic benchmarks that everyone uses. And when you try with a small data set, you may find some different behavior. So I usually have these two types of problems. One, using a very small data set, and when using a very simple model. So usually I have to use some type of optimization to find the best parameters, and then find the best solution. What you can do as well is propose your own solution that works better for your case, and then publish. I think one of the areas that have more contributions to noise label is proposal of new losses, because it's very easy, not easy, but compared to more complex ideas, it's more straightforward to propose a new loss function than a new training method. Okay, so this one, it's almost finishing. The results look interesting. Look into the test accuracy. The train accuracy, it seems like the results are pretty bad. But now here, I'll just plot. Press Shift Enter, and what you can see here I'm just plotting the test accuracy, okay, from 70% to 100%. And what we can see here is that when we tested the baseline with cross entropy for 70% noise rate, it had this behavior that it starts increasing, it starts to fit the samples, and then there is some overfitting. So if we had continued until 100 epochs or 150 epochs, what was expected to happen is that this test accuracy from the baseline using cross entropy, it would decrease maybe until 70% or lower. And using our robust loss, it has this behavior that the active passive loss had. It usually has a much slower convergence, and you need more epochs to have the convergence of the models, but the results are more constant and they are better. So we had from the clean data set results around 95, and we had now how much? 88. And compared to the baseline with noise, we improved maybe 5% here. Okay, so this was a very simple solution. You could also try the other losses that they propose in the paper and try different parameters, and maybe you can find better results than this one. It's just a matter of trying different parameters and loss functions. But that one that I used, it's one of the best that they show in the paper. And although I tried the parameters that they said, the results are not as expected, so I had to find my own parameters. Okay, so this was one of the solutions. I want to show another solution that is related to small trick loss. The small trick loss is that idea of trying to identify the noisy samples based on the loss values. So here I'll show how is the behavior of the clean and noisy samples for our noisy data sets during the training. So here I'm just identifying what are the noisy index and the clean index. And then I'll show the logs from not from this active passive learning training, but our baseline with cross entropy for 70% symmetric noise. So what I'm showing here is the histogram of the clean samples and noisy samples in the end of the training. So that means that even using cross entropy, at least for this data set, that's a more simple problem, more simple data set. You can try to split the data based on the loss value. And this is in the end of the training using 70% noise rate. In the beginning of the training, it's not easy. Like in the very beginning of the training, you would have something like this. You can't do anything, but as the model updates its weights, it gets easier. And as long as it keeps training, it gets more easier. Okay. Usually, it's not so easy to split the data for 7% noise rates. Usually, you can do that for very low noise rates, like maybe 20%, 30%. We can do that for 70% because MNIST is a very easy data set. But if you run for CIFAR 100, for example, CIFAR 10, you won't expect to have this kind of histogram for noisy rates above 50%. Okay, but this is to show that at some point we can use some kind of splitting based on the loss values. And I also want to show how is the average loss during the training. So here it shows that the average loss of the clean data set, it's quite different from the noise data set. The model easily fits to the clean data set. And again, this is a very good scenario because we are dealing with a very easy data set. But we don't expect to be that easy to separate with a more difficult data set. But at some point, we can have some kind of hint of how can we split the data. And this kind of thing is known as the small loss trick, because people try to use this to find the clean samples. And what that paper from Arazo does is to use a mixture of Gaussians based on distribution. We won't initially have access what are the noisy and the clean samples, but without knowing what are the classes, we'll use the mixture of Gaussians and try to split the data. And that's what we are going to do. So our idea is we are going to use a mixture of Gaussian during the training. At every epoch, we'll apply the mixture of Gaussian and get only the predicted clean and remove all the noisy samples. So if we get only the predicted clean, is it possible to improve the results? Let's check it. So to achieve this, I had to do a little modification to our train test method. So I created another one that's train test filtering. That's the same idea of the previous one, but I will do some filtering during the process. So at every epoch, I will do the train epoch as I did before. So this won't change. And one important thing is that eval method. So this eval method, it's important now for filtering, because now I'm using the mixture of Gaussian, and the mixture of Gaussian will return the probability. So I think this line was in the previous code, but was not important. And this one is important because I'll use the probabilities to help me to filter the samples. So I'll just check this eval just to show you how it works. So I have it here. So the idea of this method is that it will calculate the loss for all the samples in my training set. So this will loop all the samples and calculate the loss, the cross entropy loss for everyone. And then it will normalize the loss to be between 0 and 1. And with the losses, it will apply the mixture of Gaussians. It's a two-component mixture of Gaussian, and it will use it to fit all the losses. As a result of the mixture of Gaussian, it will give the probabilities of a sample to be classified as clean or not. Actually, here, what I'm getting the mean, the lower mean, the argument that minimized, because in that histogram, if we look at, let me show again. If we look here, the clean samples are this distribution with the lower mean. Okay. So here, the output of the eval, it will give the probabilities of each sample to belong to the clean set. So this part of the testing set is the same. And here I do the filtering. So here I'm using the if, because I want to start filtering after the model has learned a little bit about the samples. Because here, for example, if I start splitting since the beginning of the training, the model doesn't have learned enough to permit a clean split. So I need to have a kind of warm-up phase just to train the model a little bit and start splitting the model. So I'm using just a few epochs. I think I'm using 10. Yeah, I'm using 10. So before this warm-up of 10 epochs, I will train the same way as I did before. And after that, I will start flipping. So I'll get all the samples which have the probability above 0.5. If I want to be more strict, I can increase to 0.8 or something like that. And by doing this, I'll get all the index with probability above 0.5. And then I'm using this class here from PyTorch library, that you just give the training set and the index, and it will return a subset with those index. So I want to have a loader, a data loader, only with these samples that were classified as clean. So I'm getting the subset here, and I'm generating a data loader again. That is this clean data loader. And then I'll say that my train loader is the clean data loader. And next time it enters the loop, it will use this train loader that now is the clean data loader. So by doing this, when it trains the epoch, it will train only with the clean samples. So I will reduce the wrong information that I'm giving to the model. Now just a remind, this new clean training data, it might have some noisy samples in the middle because the splitting is not perfect. So it's expected to have some noise. Okay, now I'm gonna run the same experiment with 70% noise rate. Okay, I didn't run this cell. Okay. Okay, so it started running. This strategy of using the small loss trick, it's present in most of recent papers from state of the art. Usually they try some strategy, adding some kind of regularization to the noisy samples, because here we are using just the clean samples. We are not using the noisy samples for anything. So at each epoch here, it would use around 1,000 samples or 800 samples from all my training sets. So there are a lot of samples that are not used when I start filtering. So some ideas is to use that data augmentation strategy, the mix up, to combine the clean samples with the noisy samples. And also you can add some kind of regularization using the noisy samples. So for example, another strategy is to calculate the entropy for the noisy samples to try to make the prediction more confident. So the best methods are those that use the clean data set and the noise data set at the same time to train the model. So here we started the second stage with the filtering at this part, and that's when we got a big improvement from 71 to 75. You can see it was improved slowly, and then it had a big improvement here. And okay, it's almost finishing. Yeah, the results looks better. And now I'll plot comparing all the previous experiments. Okay. So we have here the results from the baseline with noise, the noise that's red, the clean that's black, and the new one that is trying to remove. So it started much better than the experiment with the active-passive loss. And here in the end, it is better, but we might have to run a few epochs more to make sure what is the better strategy. But by the less accuracy that we have that using this strategy of removing, it increases the results more than the other one. So here in the end, we have 89, and the previous one we had 88. So we had an improvement of 1%. So you can play with these different strategies. You can try to combine removing samples with the active passive loss, or to try some other losses, or try some kind of data augmentation, or try some ensemble approach, training two models at the same time. There are many options. Here in the tutorial, I try to show some very simple experiments with a small training set, with a simple model, with very simple solutions that are easy to adapt. But if you want to use a more complex solution, like from the last papers from noisy labels that are state-of-the-art, I would suggest looking to the Videmix. The Videmix is currently the state-of-the-art, at least until this month or until the end of the year. I'm sure that by the beginning of the year, another new strategy will appear, and we will have a new state-of-the-art. These areas change very fast. So one good thing about this area is that very easy to run the codes. People usually publish on the biggest conference, such as CVPR, CCV, CCV, NIPS, and all of them, they provide code most of the times using PyTorch. So it's easy to compare to their approach. It's easy to implement, to test, and it's easy to propose new solutions as well, because they provide the code and you can do this kind of tests. The only thing that it might be a problem is that you maybe will need some machines with GPUs to run big data sets, but that's a common problem in the area, and we all have these problems nowadays. Okay, thank you very much. I hope I have helped you to understand a little bit more about noisy labels. And this code is available in my GitHub. You can test by yourself. If you have any question, you can send me an email, and I'll be grateful to help you.
All right. Thanks a lot. Well, we should. Yeah, we apologize for running over time. We're a little bit late, but anyway, yeah. So we didn't get any new technical question in the YouTube chat, but yeah, I think this was very interesting. I was just gonna comment that my results with the active passive loss were a little bit better than the ones you showed.
Oh, like really?
90%, which was bad, because then when I ran the noise removal, the approach that removes noise afterwards, the gap was much lower. So with noise removal, I only got up to 83%. So I might have tweaked something in my local copy, which made it go wrong, but maybe it could be just a matter of these being a stochastical method, right? So
yeah,
random things like on how the samples are, well, the parameters are initialized and so on. So, I mean, I guess I should run several times to see.
Yeah, calculate the average and everything. It's part of it. I just wanted to show a simple solution that it was easy to understand, but actually, like the state-of-the-art approach, there are more complex, but they give even better results. So that was just to show an easy solution.
That's great, and the code does look really simple. So yeah, I appreciate that. It's really nice.
Thank you.
And I think the thing I most liked about this whole thing is that you don't actually tell the system which samples are wrongly labeled. I mean, the last method you showed has a way to guess which ones are mislabeled, but none of these approaches actually have a supervised means of doing that.
Yeah, you never know what are clean and the noisy samples. So the interesting part of this area is to try to propose an algorithm to have a guess of what are noisy and noisy or clean, and how to deal with the noisy samples if you just remove, if you try to use some information with them. So that's what is interesting in the area, to try to find what is clean and what's not. And just to like talk a little bit about what people are doing in the area, like for the next year, they are going more in a direction of using self-supervised training, using contrastive laws. So instead of just using a semi-supervised approach, they are going to an unsupervised approach. So they try to do a clustering with the sample. So you don't need the labels. So you can have a high noise rate, and you do some kind of clustering, but using a contrastive laws, a self-supervised approach, and then use data pre-trained to cluster the features, and then use the self-labeled samples in a supervised way. So that's a way that people are going for dealing with noisy labels, because usually for low noise rates, people can have very high results. So that's why people are going for 9% noise rate. That's something insane to imagine a data set with 9% noise rate. But that's what people are doing now, going for self-supervising strategies.
Okay. I guess this is the end of the tutorial. So if you have do you have any final remark, anything you would like to say?
I just would like to thanks everyone for watching the tutorial in a Saturday afternoon, and for all the staff from SIBGRAPI. For thanks to you, Theo, for conducting this tutorial, and a special thanks to and also the host. I don't know the name of the student that was showing the slides, and to Gustavo Carneiro, that's a co-author of this tutorial, and to Fabio Faria, that's the other author from the other tutorial. He was the one who encouraged me to submit this tutorial, and he was with me in Australia doing the postdoc. So a special thanks to everyone from University of Adelaide, and also to my colleagues from Universidade Federal Rural de Pernambuco. Thank you, everyone.
All right, thanks a lot. Well, I'm very grateful for you. You gave a very nice talk, very well organized and didactic. And yeah, so thanks to you, Felipe, to Gustavo Carneiro, the co-author. I also would like to thank the anonymous student from UFPE, right, from Pernambuco, who is helping us with this. I still don't know his name, or his or her. Or his, yes, of course. Sorry. So I would also like, since this is the end of the tutorial, the other tutorial has already finished a while ago. So I would also like to thank Fabio Augusto Faria, who submitted the proposal for the other tutorial, which got accepted. Also in co-authoring, with Gustavo Carneiro as a co-author. So again, I'd like to thank Saskia Groenewegen from Ordina in the Netherlands for co-chairing this. I'd like to mention again Lindeberg Pessoa Leite, who was the chair in the other tutorial with a very short notice, and the reviewers. Very quickly, sorry for running out of time, but I think I should mention them. So there is Antonio Oceas Carvalho Filho, and Flávio Henrique Araújo, Romuel Rodrigues, Veloso Silva. So all of these from UFPI, Universidade Federal do Piauí. So Lindeberg was also one of the reviewers from the UNB, University of Brasilia. Alexandre Zagueto from Sony Entertainment, Wolfgang Hurst from Utrecht University in the Netherlands, and Rafael Bidacha from Technical University of Delft. I should also thank my wife, who has been busy and she kept me free from babysitting duties this afternoon while we're here. All right. Thank you all. I think that's the end. Oh, the name, André Vieira. So he's a PhD student at the
Informatica Center.
Centro de Informática, right?
Yeah.
Informatics Center in the Federal University of Pernambuco, right? He was anonymous, right? André Vieira. Okay. Thank you very much, André, and thanks everyone for watching.
Thank you, everyone.
Many of you carry on with SIBGRAPI events tomorrow and the next days. Thank you.
Thank you.